Hey everybody, welcome back. Today we're going to start lesson 2 in chapter 3. It's about linear functions. Today we're just going to do the first half of it and then we'll wrap up the next half of it on Thursday. Here's going to be our general objectives, what we're going to be trying to do today, the questions we're going to be asking ourselves. How can we determine if a function is linear or non-linear? That's going to be a key distinction we want to hopefully get pretty good at. How can we tell if something is linear or non-linear? And then some objectives, what we're going to try to accomplish. This is the one we're going to try to do today. We want to try to identify linear functions using a graph, using a table, and using an equation. The second objective here we're going to save for Thursday, where we try to graph linear functions using something called discrete and continuous data. We will save that for the next one. So today we're going to focus on how we can tell if a graph is linear or nonlinear, depending on if it looks like a graph, if it looks like a table, or if it's in the format of an equation, because they can give it to us in all these different formats, and we need to figure out how you can determine if it's linear or nonlinear, depending on which format that it comes in. So I think the easiest ones to determine are the graphs. I'm going to skip just a little bit ahead here of my actual notes. We're going to hold off on this for a minute. How can you tell if one of the graphs, how do you tell if a graph is linear or nonlinear? Pretty easy. If it's linear, right? Linear, it's going to look like a line. I mean, the word line is right at the beginning of the word linear. It's going to look a lot like a line, but it has to be non-vertical. It cannot be straight up and down. A non-vertical straight line. When I say a straight line, you could draw it with a ruler, and you would not have to pick up the ruler at all. Another characteristic of a linear graph, it has a constant rate of change or a constant slope, right? It goes up, and if it starts going up, it stays going up at that same rate. It doesn't like go up gradually and then all of a sudden shoot up really high, or it doesn't start going uphill and then switch to downhill. It has a constant, consistent rate. If it starts going down like this, it's consistent and it stays like that the entire way. It doesn't start and then change and go steeper. It doesn't flatten out. It doesn't go up and down and up and down. It has a consistent, constant rate of change. The slope does not change at all throughout the graph. So here's some examples. These all are linear, completely straight. It has the same slope. This is a linear graph right here. This is also linear. It's straight across. This would actually have a slope of 0, but it's not going uphill. It's not going downhill. It is going to pass the vertical line test. Remember the vertical line test that we did the other day? Here, the graph is going downhill, but still linear. It's still a constant rate of change. It would pass the vertical line test. It is a straight line. I could draw it with a ruler. These are all linear, right? Linear graphs. The opposite is going to be nonlinear. They're pretty easy to determine. Nonlinear means it is not a line, right? I mean, I guess technically this is a line, but it doesn't meet this qualification, right? This fails the vertical line test because the vertical line touches that an infinite amount of times. Anything that has curves, anything that starts going uphill and then switches to downhill, here where it starts, this part goes uphill and then this part goes downhill, none of these are considered linear. This would fail the vertical line test, right? Remember that from the other day? Look, a vertical line hits it in 2 places. This is a function, but it is not a linear function, right? This is a non-linear function. This is not even a function. So sometimes they are functions, sometimes they are not. This is actually a function, but it is non-linear because it is not in a shape of a line. This is not a line, and this is not a line either. I mean, this is a line, but it is not, it can't be vertical, right? This has a different slope. Here it starts going up, then it starts going down, then it starts going up again. None of these are consistent. None of these are straight lines. You could not draw any of them with a ruler except for this guy, but this guy is the only exception because it is not allowed to have a vertical line. That fails the vertical line test. So these are linear over here. These 4 are non-linear. Okay, how can you tell? I'm going to save this equation thing for later. How can you tell if something is a function or not, is a linear function, if you look at a table, right? These 4 over here are all tables, X and Y tables, input-output tables, function tables, whatever you want to call them. This is actually what the regular math class learned earlier this week as well. So it's kind of weird that our lessons are kind of overlapping here. How can you tell if something is a linear function? By looking at a table. Now, could you technically take out a piece of graph paper and graph all of these and see if they fit as linear or nonlinear? Sure, but who wants to graph something that goes all the way up to 36 or 35? Or some of you don't even want to graph something that goes to 16, right? No one wants to do that. So instead of having to graph it, what you can do, if I zoom in a little bit, is try to find the rate of change, right? Try to find the slope, see if there's a consistent rate of change. When I say rate of change, look what's happening here. Do you notice a pattern to get from one x number to the other x number, one input to the other input, right? This is the domain. I'm looking at the domain right here, these input numbers. From here, from 3 to 6, you're adding 3. From 6 to 9, you're adding 3. From 9 to 12, you're adding 3, right? It has to be adding and subtracting. You cannot do this with multiplying or dividing. It has to be adding. And then you look down here with the y's. Okay, is there a consistent pattern with the y's? The outputs, right? These are also called the dependent variable. This is also called the range. All of these are kind of synonyms. Here you're going -6, 36 down to 30. From 30 to 24, you're doing -6. From 24 to 18, you're going -6. So this is consistent, right? We have the same pattern all the way across. This has a constant rate of change, right? The rate of change is actually, if you really want to know how to find it, the rate of change, you do the change in the y over the change in the x. That's actually also how you find slope, which we'll learn a little bit later. So in here, if you look, in each one of my examples here, the y's went down by 6 and the x's went up by 3. Down by 6 over 3, right? We could reduce that. The second example here, down by 6, the x's were going adding 3. In my third little category here, the y's were going down 6, the x's were going up 3. So -6 over 3, this is actually the slope. We've technically found the slope. So is this linear? Did I have a constant rate of change? Was it the same every single time? -6 over 3, -6 over 3, -6 over 3. All of those are the same. So this is definitely linear. Is this linear? Yes. This one is linear. Letter A is linear, right? We had a constant rate of change. Now maybe let's see another example. Let's see if they'll give us one where it is not constant. Let's try letter B. Here on the x's, this doesn't take very long. From 1 to 3, that's +2. How do you get from 3 to 5? +2. How do you get from 5 to 7? +2. Okay, all those are consistent, so that's looking pretty good, but we've got to check the y category, the output here. From 2 to 9, that's +7. From 9 to 20, that's +11. From 20 to 35, that's +15. So I feel like this is definitely not going to work, right? If I want to do a quick double check, look at each little comparison here. On this one, it's 7 over 2. So the first example is 7 over 2. The second example right here, 11 over 2. These are not the same, right? This is not going to work. And then the third one is also different as well, 15 over 2. None of these are the same. In order for this to be considered linear, it has to be like the last one where they're all the same. And these are all different. So is this linear? No, this is not a linear graph. This is non-linear. Non-linear on letter B. See the difference between those two? Okay, same thing on C. From here, this is adding 1. From 1 to 2 is adding 1. From 2 to 3 is adding 1. And then down on the bottom, 3 to 5, that's adding 2. 5 to 7, that's adding 2. 7 to 9, that's adding 2. When the whole thing is consistent like this, the answer is definitely going to be yes. But just to double check, my rate of change is right here. Here it is. 2 over 1 is the first example. Here's my second example. Same thing. 2 over 1. The third example, boom, 2 over 1. They're all the same. 2 over 1, 2 over 1, 2 over 1. So yes, this is linear. Letter C is linear. And then our last example down here, letter D. I'll go ahead and erase that to give myself some room. These don't always have to count by ones. Sometimes they'll skip and jump around. So these are all counting by ones, +1, +1, +1. And then out at the bottom, 16 to 8 is -8. Don't you dare say dividing by 2. I know it is dividing by 2, but when you're looking at the slope or the rate of change, you have to do adding and subtracting. So don't look at that and say, oh, it's dividing by 2, because I know it is, but when you're doing this, it has to be adding and subtracting. So -8, -4, -2, these are all different, aren't they? The first example, -8 over +1. That's going to reduce to negative 8. My second example, negative 4 over 1. That obviously reduces to something else. That reduces to negative 4. And then the last one, negative 2 over 1. None of these are the same. They all three have to be the same for it to be linear. So here's another one that is non-linear. Okay, so that is how you determine if something is linear or nonlinear by looking at a table of inputs and outputs, domains and ranges, x and y's, independent variable, dependent variable. You just look at the pattern and then you go from there. Okay, finally, and this is going to be maybe the hardest one. I don't know, it's not super hard. How can you tell if an equation is linear or not? Linear equations can be written in this format, y equals mx plus b. Now, sometimes 8th graders come to me and they've already heard of this. Other times you've never heard of this, and I don't know what you guys did last year in 7th grade. This format is a very famous format. It's called slope-intercept form. This m really represents the slope. The b represents the y-intercept. We'll learn that a little bit later if you don't know that already. The x and the y are always in there. So if it is an equation that can be written like this, it is considered linear. Okay, here's some examples. I just want to go through these, and some of these are kind of crazy examples. They're normally not this hard. How can you tell if something is linear by just looking at the equation? Can it be written like this? This is the format we're looking for. So like something like this, y equals 2x plus 5, or y equals 1/3 x plus 2, or y equals, it can even be negatives, right? Negative 3x minus 5, right? All of those would work. That's kind of the format we're looking for. Now, these are a little bit crazier. They went kind of extreme on these examples, but could we technically write some of these in this format, y equals mx plus b? Like this one, this first one, there is no x on there, but is that okay? Could I technically write this as y equals 0x's plus 3.8? And doesn't that kind of match this, right? 0x's is kind of the same thing as just 3.8. So this is actually going to be okay. This one is linear because you could write it as 0x's. And I know this is kind of a hard, these are some hard examples. Square roots. Do you see any way that you could write this as a square root? No, square roots are illegal. If you ever see any square roots in here, I don't know if you know what a square root, the graph of a square root looks like, but a graph of a square root function is not linear. This is not going to work. You cannot have a square root. You cannot have a cube root. You cannot have any exponents other than just x to the first power here. So here's another example. This is not going to work. Is there any way to write this so that it looks like this? No way, Jose, right? You cannot have the x as an exponent. You cannot have even like x to the third power. That would not work, even if it was flipped around where the 3 was the exponent and the x was the base. You cannot have crazy exponents on these. This is not legal, right? There's no way to write this like that, right? This has the x being multiplied by something, not being the part of a dividing question. The x cannot be in the denominator, right? Because, right, if you think about it, this couldn't equal 0. If we made this 0, now all of a sudden the question is impossible because you can't divide by 0. So x cannot be in the denominator. These are all bad examples. None of these are going to make lines. I actually think this next one is good, right? Could we technically distribute this one? Could we do 6 times x? Could we do 6 times 1? Yeah, so look what this one actually is. Y equals 6x minus 6. Doesn't that right here, y equals 6x minus 6, look a lot like this? Y equals something x plus b. Excuse me. Whew. I had to sneeze. This is actually good. This one is linear because whenever you distribute it, it looks something x plus or minus something at the end. Here's another dead giveaway that this is not going to work. Anytime you see an exponent that is not equal to just x to the first power, you know it's not going to work. Non-linear on this one. Technically, you could have solved this for y, like you could have moved some stuff around, but it still wouldn't work. This is no good. This one, I believe, is okay, right? Could we put a 1 on here and make it y equals 1x plus 9? Doesn't that look like some of my examples up here? Yeah, it does. And so this one is linear. And then one more I wanted to show you. This is very kind of crucial. Is this y equals 3/5 x kind of the same thing as this? yeah, it's kind of like the same thing as y equals 3/5 x plus 0, right? So this is okay as well. And I want to make a quick point here before I stop. Notice the difference between, I'm going to use a different color here to highlight this. Notice the difference between this one and this one. Very important, right? The x cannot be in the denominator. That is illegal, because if you plug 0 in there, you could not divide by 0. The x can be in the numerator of a fraction. That is okay, because if I put 0 right here, 0 times 3 is 0, and I can do 0 as the numerator. So if the letter x is in the fraction, but it's in the numerator, that is fine. For example, something like this, y equals x over 7. That would be okay. This would be linear. This is technically the same thing as 1/7 x, right? The slope is 1/7. You go up 1 over 7. So the x can be in the numerator. If the x is in the numerator, it is cool. If the x is in the denominator, that is not cool, because you cannot put 0. If you tried to plug 0 in here, it wouldn't work. It would be impossible. And so that's one big difference I wanted to point out today. Okay, so square roots, illegal. Exponents that are not x to the first power, illegal. X in the denominator of a fraction, not going to work. Anything that's not to the first power, not going to work, right? Square roots, squared, something to the x power, x as the denominator of a fraction, all of those are not going to work. Those are non-linear. But if it's just y equals a certain number, that's cool. If it's y equals a distributing question and you distribute it and you don't have any exponents, you don't have anything weird, it looks kind of normal like these over here, that's nice and that's going to work. And these down here work as well. The x can be in the numerator, not the denominator. Okay, I'm going to stop right there. We're going to try some questions on the Big Ideas Math site. I'll put the check on there if you want to go back and check some of your answers, because I know this is kind of hard to do over the phone and over video. So I'll catch you in another one, guys. Good luck.